Let f of xy equal 2x to the power of half, y to the power of half. It's subject to our two constraints listed here. We have constraint 1 and constraint 2. Now, these constraints are inequalities that are less than or equal to the budget, so Kuhn-Tucker will work. But that said, there's one other qualification to Kuhn-Tucker working, and that is that our x and y values have to be positive. So that's something to be mindful of. If we use the Kuntucker approach, we can only accept the positive x and y values. This is of particular note for a question like this, as our x and y values are squared. So sometimes we can have multiple solutions. We will only take the positive solution. So now I'm going to set up my Lagrange equation. Lagrange of x, y, we have two constraints, so I have lambda 1 and lambda 2. So the function I'm trying to optimize is going to be 2x to the power of half, y to the power of half. Then I have my constraint 1 times the budget, 800, minus the constraining values 2x squared plus 2y squared. So minus 2x squared minus 2y squared. Plus lambda 2 times my budget, 56, minus my constraining values, 2x plus 2y, so minus 2x minus 2y. So there is my Lagrange formula. Next thing I'm going to do is I'm going to do the derivatives. So the derivative with respect to x, for my first term here, I get 2 times the exponent half gives me 1. X to the power of half minus 1 is negative half. Y to the power of half. Plus lambda 1 times the derivative of this constraint, which will be negative 4x lambda 1, times the derivative of my second constraint. So that's going to be minus 2 lambda 2. I have the derivative with respect to y. So that's going to be, for the first term, 2 times my exponent half gives me 1. X to the power of half. Y to the power of half minus 1 is negative half. Now, for my second term here, the derivative of negative 2y squared is going to be negative 4y lambda 1. For my second term here, or my second constraint here, I have negative 2 times times constraint, times lambda 2, I can say it, negative 2 times lambda 2. Then I have my derivatives with respect to lambda 1. That's going to give me my constraint here, 800 minus 2x squared minus 2y squared. And then I have my derivative with respect to lambda 2, which is going to be 56 minus 2x minus 2y. So now I'm going to start doing the Kuntucker approach, where I assume one of the constraints is naturally binding. So which constraints do you want to assume is naturally binding first? So we're going to assume that lambda 1 is equal to 0. In other words, that constraint 1 is naturally satisfied when we optimize with constraint 2. Okay, so if that's the case, then my lambda 1s are going to be 0. So this will be 0, this will be 0, and this would be non-existent. So setting these derivatives to be equal to 0, I have 0 is equal to x to the power of negative half, y to the power of half, minus 2 lambda 2. I have 0 is equal to x to the power of half, y to the power of negative half, minus 2 lambda 2. And I have 0 is equal to 56 minus 2x minus 2y. Now solving for this system of equations, here I would have 2 lambda 2 is equal to x to the power of negative half, y to the power of half. So therefore, lambda 2 would be equal to half x to the power of negative half, y to the power of half. For the second equation here, I would have 2 lambda 2 is equal to x to the power of half, y to the power of negative half. Therefore, lambda 2 would be equal to half x to the power of half, y to the power of negative half. Now, setting my lambda 2's to be equal to each other, from the first equation, I had half x to the power of negative half, y to the power of half. And from the second equation, I have half x to the power of half, y to the power of negative half. So now my halves cancel each other out. I'm going to rewrite this as y to the power of half over x to the power of half is equal to x to the power of half over y to the power of half. I can cross multiply and I get y is equal to x. So now from here, I'm going to substitute this into the third equation. So I get 0 is equal to 56 minus 2x minus y is equal to x. So that's going to be 2x. So this gives me 0 is equal to 56 minus 4x. Moving the 4x to the other side of the equation, I have 4x is equal to 56. X is going to be equal to 14. Now I know that y is also equal to x, so y will also be equal to 14. So now what do I do next? Now we have to check our constraint. So here we had assumed that constraint 1 was naturally being met. So we're going to grab our constraint 1 and we're going to check it. So we're going to check constraint 1, that 2x squared plus 2y squared is less than or equal to 800. So I have 2 times my x value of 14 squared plus 2 times my y value of 14 squared is less than or equal to 800. This gives me 784, which is indeed less than 800. So both constraints are satisfied. Which one is binding? Which constraint did we use in our analysis? We assumed constraint 1 was 0, meaning it was non-binding. Constraint 2 is binding. Okay, the last thing we would do is we would solve for what f is. So I'm going to take my equation for f. F of x comma y was equal to 2x to the power of half, y to the power of half. So I'm going to substitute in my x values 14 to the power of half times 14 to the power of half. And what I get is f max is equal to 28. And it's when x is equal to y, which would be equal to 14. This would be our critical point, 14, 14, 28. Questions? In answer to your question, knowing which constraints are to be assumed to be 0, sometimes a good way is to look at the function itself. So when you look at a function and you see that it's weighted towards one variable. So in this question, x and y are evenly weighted in our function. Both are to the power of half. So then what it would come down to is looking at these sort of relationships. Are they weighted more in one of these? No. So then at the end of the day, this one would be really hard to assess by because as we saw, x is equal to y. They're evenly weighted within each of these constraints. It's not an easy one to do, but say you had a function like f of xy is equal to 2x squared y. Now we know when we look at a function like this that x, any addition to x is going to make f increase a lot faster. So x is more powerful at maximizing f. So I know that I want lots of x and less y. But that depends on the costs. So if my constraints were x plus y is less than or equal to 50, or 0.5 x plus 2y would be less than or equal to 60, I could kind of look at this and get a feel for it and say, this will probably be my more binding constraint because I want lots of x. I don't know if that makes sense. It does take quite a while to get a feel for it. Thus, we have a formalized process, but those are some of the things that we could look at.